LGK, can you see my screen? Good. Misha, can you see my screen? Good. Right, let's get to work. So, um, I'm going to be moving extremely fast. Try to just ride with me. I'll reduce all the explanations because of time. I have targets to meet, so I'm going to try to be pushing all of you every single day. Right, so I'm going to be writing important things that you must know, and then we'll see how far we can go. Last time I told you that when you're going to be doing this chapter, remember, this chapter is chapter 3. I don't want to speak to my, it's very easy for me to talk to myself until the lesson finishes, then we go, and I've really made no change. I don't want to be that guy. What I want to do is by the end of this lesson, I want all of you to have something that you can move with. Look, students, this is chapter 3 out of 6. Physics only has 6 chapters. We should not spend forever doing physics. We would have done wrong. We should just identify the tricky parts, we do them well, and we move on. Physics and chem, we shouldn't spend time. We should do them as far, even maths. Okay, we have to be consistent. So I'm going to be a little bit hard on you, and I know you guys can manage. We have only 6 chapters. This is chapter 3. Let's quickly go through it. So I'm starting with some hard things. There are experiments that you must know, as I showed you last time. Okay, the question is not closed. It's in the computer. I should have loaded it before the lesson so I can remind you. But there are experiments that you are asked, and frankly speaking, there are 5 experiments that you must know for you to say you're done with this chapter. 5, and they can ask you to set up one. So you're going to spend a lot of time studying experiments, polishing yourself up. I'm going to give you a lot of questions to make sure all of you are good at that. There are 5 experiments. 2 are for light, where you do an experiment to prove reflection, an experiment to prove refraction. Then you have 3 experiments for sound. Okay? And maybe let me just make you write them instead of me explaining. Can you write the 3 experiments? Okay? I want to do less of talking, more of writing. The 3 experiments for sound. Okay? Let's see the 3 experiments that you must know. They ask, I'm not doing things that will never come. They ask this. Please, guys. The 3 experiments for sound. Okay? All of them are like testing the same idea. It's all about sound. Okay? And let me write this sentence to say, sound travels is a longitudinal wave. Sound travels as a longitudinal wave, okay? We can use, write with me, we can use its speed. I'll also talk about echoes very soon. We can use its speed and reflections to measure things. Okay? We can use its speed and reflection to measure things, rather. The speed of sound and its reflection. I'll tell you some things. Write for me here to say, the 3 experiments for sound are, then you put up. Simon, LGK, where is Simon? But he does physics, right? Yeah, try and call him. If you can't, then I'll reach out to his mom. Oh, I had already called. It's fine. Hi. Yes, please check on Simon for me. Yes, for the lesson. Thank you. Right. We continue. I think LGK will come back. I'll be looking, eh? Sorry, just one more. Thanks, LGK. Appreciate it. Hi, Doc. Good evening. Please check on Seth for me. He's not in class. Thank you. Right. The three sound experiments are now, I'm looking, we continue, okay? The three experiments for sound are number one, okay, let me write them like this. Experiment, then here I'm going to say the main idea, because I don't want you to leave the main idea. First experiment, I'm going to be writing fast. So try to write, remember I told you when you want to write fast, this is how it is in lectures in university. So guys, I'm training you here, okay? Simon, in case you don't know what is going on, we are wrapping up this chapter 3 waves, okay? We want to know all the big things that could potentially cost you marks. So we know that we need to make sure that we know about light and we know about sound, okay? That's the main thing. We need to know something about waves, general things about waves, to say what is a transverse wave, what's a longitudinal wave, blah, 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 some basics. Then after you know the basics here, you start diving deep into it. You study light, then you study sound. They are different. When you do light, you need to be good at ray diagrams. You need to be good at electromagnetic spectrum, the uses, the dangers, okay, and then you need to be good at dispersion of light, then refraction. So we'll work again on it to make sure everybody's good there. Then for sound, you need to know the 3 experiments. Then you need to know what is pitch and then what is amplitude. Like how does frequency get affected, and then what happens when you change the amplitude of a sound wave, okay? And so I don't really want to talk about tone, but I would rather talk about pitch and volume of sound. Okay, the pitch and volume, I'll talk about it. So let's go through it. Then we do the calculations. So for sound, hey, listen, I said to be good at this chapter, look, you gotta be good at, you should know how to do light in terms of waves for chapter 3. What do they ask you? Do they ask you what light is? No. Do they ask you what you are thinking? No. They ask you what is written here. Ray diagrams. The electromagnetic spectrum. You should know all the 7. VUXI. Radio, microwave, infrared, VUXI. What is it? Visible light, ultraviolet, X-ray, and gamma ray. All those, you must know them. And then you must know refraction, dispersion of light. I'll make sure you guys are good at it. Then sound and blah, blah, blah. So let's go. First, we are looking at sound. We go step by step. Okay, we are not magicians. We don't finish the whole chapter by saying one word only. There has to be hard work involved. So when we say you want an A star, it doesn't mean you're going to get it easy. No, you get it hard. So let's go step by step. We want to cover sound, the sound part of chapter 3. And one of the biggest part about sound is the experiments. 3 experiments. And that's what I'm covering right now. So in case you want to know, we are doing the sound. We are doing chapter 3 called waves, and we are focusing on sound. And we are doing experiments. Huh? You hear me? There are 3 experiments that you are expected to know. Are we together? The 3 experiments are here. I say the 3 experiments for sound are: number 1, you are going to be, experiment number 1 is about measuring the speed of sound directly. Okay? We're going to be measuring the speed of sound directly to find out what? What is the main idea? What do you want to find out? Huh? What do you want to find out when you do that? You're going to measure how fast sound travels through air. Okay? You must already know that the speed of sound, let me write it here. Where should I write it? Speed of sound in air is going to be 330 to 350 meters per second. We usually use this one, 330 meters per second. Okay, this is the speed of sound in air. Okay, it depends on temperature. When you increase the temperature, it will move a little bit faster, but it's always between 330 and 350. Good. Speed of sound in air. So the first experiment will be measuring the speed of sound directly, okay, to check the speed of sound in air. Then the second one will be measuring the speed of sound using oscilloscopes. Measuring speed. You're going to learn more about this cathode ray oscilloscope at A-level physics. Measuring speed of sound using oscilloscopes. Then, okay, then you're going to be checking what we call ultrasound. You're going to do an experiment on ultrasound, or I'll say echo sounding. This is the third experiment, right? And when we talk about what they are about, these experiments, this year you're going to be use of sound waves. Okay, when we check ultrasound, you're going to be using a sound wave, of course, to do what? Use of sound waves to measure depth or to detect objects in water. Okay, you're going to look for something that sound will hit onto, either the bottom of your sea or whatever, or you're going to be checking for an object which is in the water. So, really? Yes. Wow, that's good. Yep. And then you can do here more accurate. It's just more accurate version of this. Okay? Why? Say using electronics. It's pretty much the same thing. Speed of sound. But you're going to be more accurate than you would have done directly. Are you ready? Hello? Good. Let's do experiment 1. We need to do them quickly. We should not over-glorify these things. We should not make them hard. We don't fear this. We know that we have 3 experiments. Let's write them first. Experiment number 1. Experiment number 1. Let's go for it. I'm not going to explain. I'm tempted to explain, but I'm not going to explain. Of course, I'm tempted to explain. Measuring the speed of sound directly. Okay? How many experiments, my students? How many should you know for sound? How many? Thank you. Thank you. You should know 3. Well done. Good. Let's go. The first one. So can you write here the main idea, the concept? The main idea is you're going to measure two things. One, distance traveled by sound. Then 2, the time taken by sound to travel the distance. Then, then calculate speed using the following. Speed is equal to distance over time. We are then going to calculate this speed by using the formula speed is equal to distance over time. Are we together? Are we together? Good. So we're just going to measure the speed, measure the time, then we are going to say speed divided by time. We're going to measure the distance, then we measure the time. Then we say distance over time. How much distance has it covered? How long has it taken? Then we divide them, we find the speed. So we can't guess. Speed is calculated, my friends, all the time. You should always know that. Now let's start. Apparatus, Apparatus, or sometimes at your level, it's called equipment. Whether they call it equipment or apparatus, I actually don't care. It's the same thing. We're going to use more of apparatus when you get to A level. Number 1, wooden block. You need a wooden block. So let me say wooden blocks. And I want here to say to produce sound. I'm giving you the use of them. Number 2, you need a stopwatch. And this is to measure time. Then number 3, you need a trundle wheel. I wish I had taught you chapter 1 already. I haven't, but it still doesn't matter. So when you are measuring distances, you should know that there is a rule which says that when you measure things, you must have an appropriate instrument. You can't measure the distance from Gaborone to Joburg or Midrand or Pretoria or Gaborone to Maun or Harare to Bulawayo using a ruler. No, you can't use a trundle wheel. No, you use what they call an odometer. So when you're measuring distances, there is an instrument for each type of length, each distance. Like when you're measuring things that are very, very thin, you're going to use a micrometer screw gauge. Then from there you go to vernier calipers. Then from there you go to a meter rule, which measures in millimeters. Then from there you're going to go to a trundle wheel. A trundle wheel is used to measure things like the distance for your, when they are putting your house, when you buy some piece of land and you're building your mansion, they're going to measure using a trundle wheel. So a trundle wheel is for distances like that, because you can't use a ruler, you can't use a measuring tape, it's not the best. So they use what we call a trundle wheel for such distances like the length of a house, they are choosing. So here, when we are doing the length that you're going to place your things, you're going to use a trundle wheel. Are we together? Have you ever seen a trundle wheel? Like those things that has a wheel that people move whilst holding. People who fix roads and stuff. Have you ever seen them move with something like a wheel on a stick which they move rolling like this? Have you ever seen it? Yes, that's a trundle wheel. It looks like this, something like this. then it is like this, then it has a wheel at the bottom like that. So it has a wheel. This is what they call a trundle wheel. So this is a trundle wheel. You needed to measure the distance. So you need those three. You need the wooden clock. Boom! You're going to hit them together. They're going to produce sound. And then you're going to have a trundle wheel. Now, what I want you to do is, we're not going to write that you need two people, but for this experiment, you need two people to do it. Let's now write about the measurement, the method, so that you people know the method. Okay? How we are going to try to find the speed of sound. What is the speed of sound in air? So number one, what happens is you're going to measure, don't measure a small distance, okay? Measure a large distance, not too big, large distance, about 100 meters, okay? Measure a large distance, e.g. 100 meters. This is the method. Then number two, you one person or the first person should bang the blocks together. One person bangs blocks together, okay? It's one side of this. Then the other one, who is 100 meters away, another person who is 100 meters away, write this, another person will be looking, okay, whilst you're banging the blocks. So another person will be looking. The moment they see your hands close, boom, to say you have banged, they start the stopwatch. So one person, okay, 100 meters away, the other person, okay, those 100 percent. What does it do? Number one, starts stopwatch when they see, not hear, when they see blocks hit one another. And they stopwatch when they hear sound. They stop stopwatch when they hear the sound. So when they see your hands going together, they start. When they hear, then they stop. Okay? Record the times and record the time and repeat several times. Okay? Then calculate average time from the time recordings, from the measured values. You add all of them, then you divide by how many they are. Remember, average is mean. You people know about mean. This is not a problem for you people. It's not a problem at all. Then number 6, right? Number 6, calculate speed. Remember? Or let me say calculate average speed. Remember? Average speed is just equal to the distance over the time. And you have the speed. Put it. Okay? Are we together? Now, source of error. We always need to always put the source of error. Source of error, say the human reaction time. Okay? you can say, this is because the time interval is short. So stopwatch. Okay, I'll allow you. Just let me write this. Then you can ask the question. Stopwatch errors are large. The stopwatch errors will be large. Yes, you can ask the question. I see your hand is up. You put it down. Yeah, we're gonna do them. We're gonna do them. I don't want to do them now because it will stop me from finishing. Just let's push, okay? I'm gonna do them. I'm gonna do the questions with you, and we'll see how you are gonna write it. Yes, definitely, okay, Misha. We'll do alternatives to practical papers, okay? Don't worry about it at all. Don't worry about it. I'll definitely do all types of papers. Let's quickly push the content. Let's quickly push the content. Okay, okay, Misha. Okay. Cool. Let's push. How do you let's write improvements. Write these improvements. Improvements. Number 1, repeat readings several times. Okay? This reduces the random error. Random error, which is, it means error caused by humans, caused by a person. If it's systematic error, it's caused by an instrument. And my friend, there is nothing you can do to fix unless changing the instrument. Okay? Are we together? The only thing you can do to reduce a systematic error is to change the instrument. Now let's go to second. Use larger distance, because trust me, 100 meters is too small. Speed travels at 330 meters per second. So that means it takes less than 1 second to travel from the person who's clapping to get to you. So yeah, you can use a much larger distance. Okay, this makes timing more reliable. Let's say you go 300 meters away or something, that's better. Okay? So if we say human error, human reaction time, this is how you would have written it. Let me just put it like this. You would have said, this method of measuring speed of sound in air is less accurate because human reaction time affects the stopwatch readings. So because of that, let's go to the other one. But are we good with this one, students? We are fine with this, huh? LGK. LGK, are we fine? Experiment 2. Let's measure the speed of sound using microphone. Pardon? Yes. 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 That's exactly correct. You cannot change human reaction time. Human reaction time is inbuilt in a person. So the only thing you can do is to increase the number of readings. Okay? It reduces it. The error caused by human reaction time. Okay? If you do one reading, it will be very, very false. But if you do 10 readings, it will be a little bit better. Okay? All right. Let's keep going. Let's now go to experiment 2. What you must know, errors that are caused by human beings are removed by repeating readings. They are reduced rather, not removed, but by repeating the reading over and over again. So if they say, how can we improve this? You say, take more readings. Experiment 2. Are you with me? Measuring speed of sound using microphones and an oscilloscope. Okay? Oscilloscope is a screen. Not like a computer screen, but something that is a screen. It is an instrument, but it has a screen to display the signals that are going on. So let's put apparatus. Well, let me write the main idea here. To say the main idea why you're going to be doing this is because, I want to write it the way I wrote this other one. Main idea, then I wrote like this, then I did the apparatus, blah, 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 blah. Then I did the method, then I did the source of error. Let's go. Main idea. The main idea behind this experiment is to use electronics instead of humans to measure the speed of sound in air so as to avoid the errors caused by human reaction time. Human reaction time means this. You are not going to stop the watch the moment you hear the sound. You're going to hear the sound and say, oh, then you stop. Oh, then you stop. That reaction time will affect the readings. You hear, then you say, oh, then you stop. Then you hear, then you stop. Then you hear, then you stop. So that reaction time is affecting readings. If it's an instrument, it doesn't have a reaction time. It will be measuring right there, right then. Okay? You understand? Right. Let's go. What equipment do we need? We need, let me write, apparatus or equipment needed for this. We need, number one, 2 microphones. Can you write to say you need 2 microphones? Number 2, and both of them are to detect sound. They are for detecting sound. Then you need an oscilloscope. An oscilloscope. Then you need, okay, it's there to display signals. Okay, I'll teach you a lot about an oscilloscope, don't worry. You need now wooden blocks to produce the sound. Of course, we talked about it in the other thing. You need wooden blocks to produce sound. Then you need a tape measure or a measuring tape. Why are we using a measuring tape? Because we are not doing a big distance like we were doing there. Okay? Why? Why do we need this? To measure microphone separation. You're going to separate the two mics. Then when we want to measure the microphone separation, we are going to use measuring tape. Am I being heard? Let me make sure everything is fine there in the stream. Is everything fine? Hi Seth, I see you in the stream. Well done. Hi Hannah. Good evening. Yes, so this is it. Now we keep going. We keep going. These are the things. So here it is. Method. Let's now talk about the method. So we need 4 things. Don't forget, we need 4 things. In the other experiment, you needed just the wooden blocks, the trundle wheel, and the stopwatch, and 2 people. So you needed 3 things there. The blocks to produce sound, the watch to measure the time, the wheel, the trundle wheel, to measure the distance where you would put the other person. You measure 100 meters to place the other person, 100 meters away. So you needed 3. Here you need 2. You need 4 rather. What am I saying? You need the microphones, 2 of them. You need the oscilloscope, cathode ray oscilloscope. You need the blocks, the wooden blocks. Then you need the tape measure. Okay? So the wooden blocks produce the sound. The microphones will detect it. The oscilloscope will display signals. And you're going to separate your 2 microphones a known distance. A known distance. You separate them. You measure with a tape measure to separate their distances. Okay? So let's do it. Let's now talk about how we do. Number 1, place the microphones, place the 2 microphones. I don't want to over-explain. I don't want to over-explain. A known distance apart. A known distance apart. Then connect them both to the oscilloscope. Connect them both to the oscilloscope. Connect the 2 microphones to the oscilloscope. Number 3, create a loud sound by clapping the blocks together near the first microphone. Let me say near microphone 1. You go close to microphone 1. Clap. That's it. Number 4. Oscilloscope shows. So to you, you'll be acting like the sound is at microphone 1. Okay? It's being produced there. Because you just go right close to it. Oscilloscope will show signal reaching microphone 1. Then signal also reaching microphone 2. Then are we together? Students? Are we together here? Your oscilloscope will show you these 2 signals, okay? It will show you the signal that is getting to the first microphone. Then it is going to show you. So it's like you're doing this. Let me kind of put the diagram here. It's like you're doing this. You have your oscilloscope. Okay? It's just a box with a screen. And it has these buttons and whatever. Then this is where it shows things as graphs. Okay? It's almost similar to that electrocardiograph thing, which goes dee, 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 in hospitals, showing your pulse. The way your heart is beating, the pump rate, like this. Anyway, you take the two inputs here, which are like this. One goes to the first mic, the other one to the second. So I would say this goes to the first mic, which would be like here. I don't even know how to draw a microphone. Second mic. You should know this separation here. This distance between the two mics. Sorry, I'm bad at art, everybody. You forgive me. Can you all see? You should not too shouldn't be too long, okay? Just a few. Yes, it's going to the moment it hears a sound, it will show a signal. Okay? So you can say here about 2 meters is going to be this separation between. Okay? So the oscilloscope will tell you the time at which the signal has arrived at the microphone. The moment the signal arrives at the microphone, the oscilloscope will display a signal. Are we together? Hello? Hello? Yes. I know. What is it? Simon, your question was, how do you check time from the oscilloscope in experiment 2, right? You want to know, how do I know, does the oscilloscope show it as time for me to be able to check the time difference between the two waves, the time arriving at the sound wave arriving at the two microphones? What really does the oscilloscope show me? These things you do more experiment. Is that your question, Simon, or did I not hear it correctly? Okay, so the oscilloscope does not show your sound. The oscilloscope shows signals on a screen, like waves like this. Okay? So it will tell you when the microphone detected the sound. Okay? So what happens is there's going to be you're going to see this when you get to A level, that the oscilloscope has like boxes, and these boxes, we can use them to find time. Okay? There'll be boxes. Yes, we'll use the boxes to find time. You see more of this at like A level. Here they just want you to explain. Okay? What you're going to do is, it's going to show you the first wave, then the second wave. You are going to check on the horizontal axis the separation between those two waves. Okay? The separation between your two waves. This one and another one, which will be whatever, man. Like these down, then, let me try. Like this. Let me put it in pink. It will be mountain here, so it goes down. Then, I'm just showing it. They'll be different. So you check the time difference between these two. Okay? Are we together? They'll show you, there'll be a bit of a separation between A and B. Like, let's just say that the first one starts like this, then you see the second one like this. You can see that there is a separation here. Can you see this separation? What color should I put it in? I'll put it in yellow. There is a separation here. I'm putting it in white, but you can see that there is a separation here, which I've put in red. Can you see the separation I've put in red? Yes. That is the separation. The separation I've put in red between these two graphs. You are going to convert that to a time. These you learn better at A level. How to use, it's actually nice. At AS level, the moment you'll be told that one division, which is one box, is how many seconds? So you're going to check the number of division and multiply by the number of seconds you've been told. Then you find the time. Do you hear me? Each division on a cathode ray oscilloscope, they will tell you how many seconds it is. So you will check the separation. How many divisions are there between these two waves? If there are two, you'd say 2 times. For example, a division could be 0.002 seconds or whatever. Then you'd have found 0.004 seconds. Are we together? And now you'll be knowing that these two mics are 2 meters apart. They are 2 meters apart. So you'll be now saying speed is equal to the distance between the two mics, 2 meters, divided by time, 0.004. Then you get the speed. Do you see how smart they are? These people did a smart experiment, right? Students. To say we are going to check to put the microphones a certain distance, 2 meters. Then we will check. So we now know the distance. Remember, you still use the same formula. Speed is distance over time. So this is where you get the distance here. Distance is here. Now you need time. For you to get time, you see the time that the sound took to cover these 2 meters. What do you mean, sir? The time that your wave took to cover 2 meters. Yes, how do you know it? That time is known from the oscilloscope. It will be this separation here. This separation between the two is the time it took to cover the 2 meters. Because it got to the first one, then it got to the second one. So that separation shown on you is the time difference. Are we together? So you will clap here. You come right here, then you clap the two blocks together. Simon, can you see it? You clap, pa! Then immediately this one will show you the first wave. Then the second one will now show you after. So that separation between the first and the second, use it to get time by checking how many divisions would be before you check, then you multiply by, this will be the time per division. So they will always tell you each division is how many seconds. Yes, it will be represented by the second wave. So you check the time between the two waves. You know the distance between the two waves. You need to check the time between the two waves, and you divide them together. Speed will be equal to, yes. Yes, it is definitely. And they sometimes will give you, then ask you for errors. They'll give you and they'll change something, then ask you for errors. Okay, LGK? They'll sometimes ask you for errors in here. Okay? So you must be careful. Sometimes they'll ask you for errors. I should show you the tables, man. Let me think. table of results. I should have shown you some table, how you do it. Let me say. Okay, let me put something here so that I can be. Can I do this? Record the time and repeat several times. Changing the distance between the two people. If you now want to make the table of results, let me just make it very small, okay? Make a very small table of results so that we can be able to. It would say distance between the two people. This is the first experiment. I'm back at the first experiment. Then you say time 1 in seconds. Then time 2 in seconds. Then you can say time 3 in seconds. Then you can say average time. Then distance you can try, for example, 100 meters. You do it 3 times, then you do 120 meters. You do it 3 times, then you do 140, I guess. It's better. Yeah, meters. You do it. Stuff like this, so you can repeat it like this. Record the time and repeat several times, changing the distance. And you can say, you can put a F between the two people. You can say, do experiment 3 times per distance for each distance. You do the experiment 3 times and you get the average time. So you put the person at 100 meters, then you clap, they stop when they hear, they record. You clap, they stop when they hear, they record. You clap, they stop when they hear, they record. Then you say, move back a bit, they go to 120, and you do it like this, and you'll be calculating the speed. So this is about time. You get average time, but here, when you get average time, you are going to be getting speed as well. I don't know why I should put another table for speed, because now you'll be having the distance, then average time, then you should get the speed. You see which value of speed appears the most. So put another column for speed. Then you see which value for speed appears the most. Which one is the mode? Okay, so good. So remember, I once taught you about variables, and I told you that the control variable is what we are not changing. We're keeping the same. Then the independent variable is what we are changing. Then the dependent variable is what we are measuring. So let me put, if we are to say here in the main idea, we should talk about the variables. Okay? Dependent, sorry I didn't do it. Dependent variable of this, the dependent variable in this experiment is what we are changing. This is the dependent variable. And the dependent variable here we are changing is the distance. Okay? The distance between where the sound is produced and where it between two people. This is the dependent variable. Then the second thing will be, what is the independent variable? I am using these words because you usually ask them. The moment LGK asked me about practical, I then remembered about these. Independent variable is LGK, what we are measuring, right? What we are measuring. So we change something, then we measure the outcome. We change what? We change the distance to say, move further, Then we start, then we clap, and the person hears, then records. So we will be measuring the time. It is what we are measuring. Then control variable is what should not be changed. What should you make sure you don't change? Okay? It is the location of the experiment. Location of the experiment. You can't first do it on a flat ground. Then you go and one stone stands on top of a mountain, the other one down. Then you measure the distance and you do the same thing. Hey, why are you changing location? You're affecting the experiment. Are we together? Let's go to the second. Let's go to the second experiment. Have you ever seen that time is a problem? How is it 9 o'clock? Can somebody please tell me? When did it get to 9 o'clock, guys? Do you have an explanation of how it's 9 o'clock already? I don't know why it's 9. Feels like we just started. Okay. Create a loud sound near HF. Oscilloscope shows signal reaching microphone 1, signal reaching microphone 2. Okay? Or you can say the time. Oscilloscope using, it shows time at which signal reaches microphone 1 and the time at which signal. But sir, it doesn't show the time. It shows the time using what? Divisions. You just multiply the divisions by the time that each division represents. So if you see 5 divisions, you say 5 times 0.002 maybe, then you get your 0.001 or whatever it is going to be. You understand? So oscilloscope shows you time. Shows you the time between the signals. Right? Okay. So it shows us this thing. So we can easily find the time difference. Okay. Close off these drawings. These drawings. Okay. Still on the fourth thing. Still on the fourth thing. Time difference between each. The time difference between each microphone is calculated. Is calculated. Okay? Right. You calculate it. This one minus that one. Now just write. Repeat this experiment for several distances. Repeat the experiment for several distances. Okay? Are we together? Guys? Now, if I go to this main idea, I'm going to before we talk about apparatus, I'm going to say the variables are going to be one, the independent variable. As my students, you should know that independent variable is what we change. Huh? Write this. You should know that it is obviously what we change. In the last line, we said, what should we change? The distances. Several distances, okay, between the microphones. The differences between the microphones. We change the distance between the microphones. So you say independent variable is the distance between the microphones. If they ask you, so they will not ask you in the words to say independent variable is what we are changing. But I'm telling you so that you remember. When they say, tell us the independent variable, you just think of that experiment and say, what do we change? What is it that we are changing in this particular experiment? And guess what? It's the same for both. If you go to the other one, we said the independent variable is also the distance, but it's the distance between the two people. We change the distance. In here, what we are changing is the distance between the two microphones. Between the two microphones. But it's distance for both of these two experiments. For both of these experiments, the independent variable or the dependent rather, the one we are measuring is time. The dependent variable, okay, what we measure is the time. The time. The time it takes to get to each microphone. Okay? The time it takes sound to get to each mic. Then the third is the control variable. What is the control variable? What is a control variable? What is a control? It is something we don't want to change, right? It's something which can change, but we should make sure we don't change it. And the control variable for this, it will be the location of experiment. Location of the experiment. And the microphones. Don't change the microphones. Use the same microphones, please. You can affect things if you go and change the microphones. Okay? Right. Now let's go for it. Have you written all this, students? Now, let's see the source of error. What you must know before maybe I talk about the source of error is, so how then, sir, do we do the co-equation? You must then use the co-equation. You measure the time difference, then you're going to calculate the speed. I can even put it as number 6 to say then, calculate speed. Using core equation. What is the co-equation? It is speed is equal to distance over time. Okay? Now, let me write. This method is more accurate because the timing is electronic. That is the reason why this is a better thing. There is no human reaction time in the time values. Are we together? Hello? Now, what is the source of error? The main one. The main source of error, wish I could say the main possible error. Main source of error is reading the oscilloscope incorrectly. Okay? E.g., forgetting to convert milliseconds to seconds. Because oscilloscopes will give you in milliseconds. You must know how to convert. Are we together? The milliseconds to seconds. Okay? So, how do you fix it? Improvement. How do we do this improvement? Ensure you read the time base correctly and account for it or for the scale used. Okay? Whatever scale, if they're using milliseconds, make sure you convert to seconds. That's what we mean by account for it. Am I being heard? Okay? Be careful. Students, be careful. Please. Can you do the last one? Can we do the last experiment? And we know we are done. Do you see that there's a lot of work? Imagine trying to do all this night before an exam or whatever. It's impossible, right? Ultrasound or echo sounding. Ultrasound or echo sounding. Right. Let's see the main idea behind this. Let me say this. Let me tell some people. You can use an echo to find the speed. But what you're going to do is you hold a stopwatch, right? Then you clap. Then your sound will go and hit the wall and come back. You stop it. Or you can shout, hey! Then you to go, hey. When you hear hey back, it means the echo has come back. You stop your watch. So if you say, you go on a mountain, wherever you go, you say, and there's a wall. You should know the distance between you and the wall. Somewhere far away, you say, hey! The sound will go hit the wall. When you hear it come back to say, hey, it's back, you stop. What you're going to do is, you check, this is the person. Don't draw, you don't have to draw this at me. You shout, hey, it goes, hits the wall, and reflects back. So you should know that the speed will be equal to this distance between the thing. It goes, then comes back. If you want, you're going to say speed is equal to distance divided by 2 first. Okay? Distance divided by 2, because you know that when you hear an echo, speed has traveled to and from, which is unfair for it. It has traveled 2 distances. So for you to find the distance it takes, this is a very, very important concept about echoes. Echoes is something that a lot of you get wrong. Okay? Remember, you are going to say, if you want, or let me say, usually they want you to find the distance, not the speed. They would have said, find for us the distance that this wave has moved. You're going to say speed times time, then you divide by 2. This will help you know the distance it has gone. Okay? And for speed, you are going to use 350 meters per second, the speed of sound in air. Then for time, you check the time when you stopped your watch. Hey! Then it goes, it hit back, it comes, hey! You stop your watch. So that's going to be the time. Then you now divide it by 2. You could have just divided the time itself by 2, but you can still first multiply them, then divide by 2. It's still, or to say speed times time over 2. That's another one you could have still used. Doesn't matter. Or you can still multiply them, then divide by 2 afterwards. You will get the distance between the person and the wall. This is the distance, the one-way distance if you want. You should divide whatever you get by 2. Am I being heard? Huh? One person will clap, the other one will wait for the sound to come back and stop quickly when you hear the echo come back. Then that will be the time. The speed is the speed of sound in air, which we said is 330 to 350. You can use 350. Say 350 times the time, then you divide by 2. Did you see this? I wanted to just explain that idea about echoes. Have you heard me? So we are going to be using this idea, but we are going to be looking for the depth, because we know that we are going to produce a sound. It will go to the bottom, hit whatever is there at the bottom, and come back. So we're going to use this same thing to find how far is something, how deep is something. Okay, you detect the echo that has been reflected back. You produce a sound, the echo comes back, you detect it. The time it takes for the echo to come back, you multiply it by the speed, then by the time, then you divide by 2. So the time it takes, you multiply it by the speed, you divide by 2, you will get the distance. Am I being heard? Okay. Echoes will be revealing what? The distance. Remember? That's the main idea. Echoes reveal distance. So if I can say main idea, I'm going to kind of give you the cheat code. Remember? Echoes reveal distance. Echoes reveal distance. Let's see what happens in this experiment. So the main idea is that sound reflects off boundaries and returns as an echo. Are you writing with me? We use the echo time, the time it takes to hear the echo. Okay? We are going to use it to find distances. Okay? The distance to whatever, whether it's a crack or the depth of something, or the distance an object is, or a structure which is inside a rock inside the pipe. You want to find where is that rock. We use the echo time. to measure position or distance. So write that. To measure depth or distance or position of crack. Position of a crack. Am I being heard? Or internal object. To locate it. Huh? Okay? In the lesson, I know you're super saturated. I know. You know, when you're going to tell people how hard you worked for your thing, this is what it will be. 5 more minutes and you guys are done. This is the last thing. I know you guys are super saturated, okay? Yeah, just 5 more minutes. You've worked so hard. Well done. This is the last one. I know you are saturated. I know. This is the last part. Let me see what I can do. It's actually, this is the shortest experiment, so I shouldn't give you many. They don't want you to, they just want you to know the idea. Then they want you to know the use. Okay? Yes. So they want you to know the use. So, do you guys know what ultrasound is? What we are using is we are using a type of sound called ultrasound. Ultrasound, we can't hear it. Infrasound, we can't hear it. When we say we are having ultrasound, let me just show you guys a little bit more. Just draw this chart to say, before I do main application. Okay, you guys are done. What we call ultrasound, human beings, there are 2 things that you must know about sound. Please, everybody, listen. There are 2 things that you must know about sound. Number 1, let me say this. Frequency of a sound wave is related to its pitch. Frequency of a sound wave is related to its pitch. Okay? Write this. Are you writing with me? We are saying the frequency of a sound wave is related to its pitch. Change the pitch of the song. Change the pitch of this. We have what we call the pitch of a song, right? You guys do know it? In physics, what will be changing is the frequency. Okay? High pitch, low pitch. When they say change the pitch, are we together? Let's say a bass guitar. Dun, dun, dun. Oh, bass guitar. This is low pitch. Then a scream. Ah! Or a baby crying. Meow! Meow! That's a high pitch. Or male voices are low pitch voices. Female voices are high pitch. So pitch is how we as human beings understand frequency. So frequency of sound is related to its pitch. To us, we'll be hearing pitch. When the pitch is going higher, it means we are changing what? The frequency. Okay? The frequency will be higher. So high pitch is high frequency. Are we together? Which also means short wavelength. If you are representing this type of a wave, it's a wave like this. it goes up, down, close to each other like this. This is a high pitch sound, like a scream. Then low pitch, like a bass guitar or a male voice. This is low frequency sound and frequency. And it means it has high or long wavelength. Long wavelength. When it has low frequency, it has a long wavelength. So it'll be like this. Oh my, I don't understand and a lot of things. Hello, welcome to Clarify. We are happy to have you on board for the physics lesson for 10 May 2026. Aki, is that high frequency or low frequency? Aki, if I say, hello Aki, welcome to the Clarify lesson for 10 May 2026. Is that high frequency or low frequency? No, Aki, no guesswork. Low pitch. Is this high pitch or low pitch? Hello Aki, welcome to the lesson for 10 May 2026. What is that? Low pitch, which means obviously it is also low frequency. Yes, it is low frequency. The waves are far away from each other. One peak is here, then the other one is far away, then the other one is far. That's low frequency, man. They are not very frequent. But if I say, hi Aki, welcome to the Clarify lesson for 10 May 2026. We are happy to have you in class. What is that? High pitch, which means what about the frequency? High frequency. When you see on a diagram, they'll be close to each other like that. Okay? Then last thing is amplitude. Amplitude of a wave. Amplitude of a sound wave is related to its volume. Somebody says, hey, can you stop speaking? Then you start whispering. You know what? I was thinking about yesterday. I've been working very, very hard. I need to be rewarded. Yeah, hard work never killed a man. I should keep working hard. What are you doing? You are whispering. So what type of a sound wave is that? It is a low amplitude wave. So are you with me, students? Are you with me? We say the amplitude is related to its volume. So if we are going to put like this, so let me put it like this. Low amplitude is the same as low volume. So amplitude is not related to the pitch, but to the volume. For example, if you have a wave which has low amplitude, it means your wave is just going to be going like this. It doesn't go too high. It doesn't go too deep. Yes. But if I say to you guys, listen, I need you to hear this. I've increased the volume. So I have done high amplitude, okay, of a sound wave, which means there's a high volume. You cannot afford to forget this. Come on now. Hello? No. LGK. I'm increasing the volume so that you can hear. So it'll be like this. It's pretty much the same wave, but one is just higher than the other. Okay? They have the same number of mountains, so we are not changing the frequency or anything like that. So if you look at these waves, both of them have 1, 2, 3, 1, 2, 3 top of the mountain. It's pretty much the same frequency, but one has a higher amplitude. This is the amplitude here. And look at this one now. It's 3 boxes. So it's a higher amplitude, which leads to a high volume. Low amplitude or small amplitude, okay, small amplitude, low volume. Okay? Yes? Are we together? Okay. So, last thing you must know is the uses, okay? The uses of this. Oh, I wanted to then tell you what ultrasound. All right. I was wondering why I went to tell you about pitch and frequency. All right. So there is a frequency that human beings can hear. Okay. Let's put frequencies. We want to define ultrasound of ultrasound. Ultrasound is sound that has a higher frequency than what the human can hear. Are we together? Infrasound is sound that has a lower frequency than what the human can hear. So write me to say the approximate range of frequencies that are audible, that you can hear, that are audible to humans is 20 hertz to 20 kilohertz. In other words, 20 hertz to 20,000, because kilo is 1,000 hertz. So this is the audible range of a human being, 20 to 20 kilohertz or 20 to 20,000 hertz. So this hearing range decreases with age. You can talk to your grandfather and they may not be able to hear you. It's because their hearing range is now reduced. All right. Anyway, if we then draw a diagram to represent what infrasound and ultrasound will be, you will find out that infrasound frequency would be from, okay, sorry, I'll put the frequency, or even if I put it here, frequency would be from, say, 2 hertz to 20 hertz. Then you know from 20 hertz to 20,000 hertz, you can hear. This is audible range. This is audible range. You can hear this sound. This one is infrasound. Its frequency is less than 20 hertz. Do you know when you pass 20,000 hertz, this is going to be ultrasound. Okay? Infrasound has low frequency, which also means low pitch. So when the bass is too deep, you can't hear anything. Ultrasound is high frequency, which we said it obviously means high pitch. That is why people scream when they want us to know of danger, because they know we can, when you get higher towards 20,000, we can hear you. But if it becomes too high, we can't hear. Okay. Scream so that they can hear you. Help! That's how it happens. Okay? So, ultrasound has high frequency. So, it is going to detect small things. Are we together? So, if we now write the main applications. Let me say the core idea here. Let me just write the core equation. So, ultrasound, core. So, in the experiment, ultrasound, Simon, are we together? Well done. Ultrasound travels, one, to the object, like I showed you where it goes to the wall, and it travels back again. So that means, my friends, if you want to find the total distance from you to that object that you'll be looking for, total distance is going to be or let's say the depth, not the total distance. If you want to cover the depth, this is going to be speed times time divided by 2. And speed will be using 330 to 350 meters per second. The time you measured, you divide by 2. You find depth. What is depth? It's a distance. I taught you echoes. I taught you echoes because that's the concept we use here. I taught you that when we do echoes, we divide that by 2 because we know it goes there and hits the wall and comes back. So when you want the depth is one-way distance. We know it goes down to the bottom, hits whatever object, and comes back. So when we want the depth, we divide that by 2. You're not letting me down, students. Come on now. Let's go. So this is important. So ultrasound will reflect at the boundary, whether it is the bone, whether it is the floor of the ocean, whether it is a crack in the metal. I don't care. When there's a boundary, it is going to reflect and come back. You multiply that time by the speed, divide by 2, you will know the depth. Are we together? So, ultrasound, I'm done. Just need to give you a few more. Works by detecting echoes. You know what ultrasound is. It has higher frequency than what we can hear. So we can't hear it. It's not in the audible range. By detecting echoes from boundaries. I need to do questions on this tomorrow. Trust me, I have to. Okay? It is useful because it has high frequency which means short wavelength. You have to know when your frequency is high, your wavelength is short. If it is short wavelength, that means it detects small details. It detects small details. Okay? So remember to divide by 2, okay? There is a return journey there. There is a return journey. So remember to divide by 2. So right now to say, ultrasound, before I just give you the uses and we are done, reflects at boundaries. So it detects small details. Why? Because it reflects at those boundaries. It reflects at boundaries. Okay? Reflects at boundaries. Examples being, examples 1, the bone. 2, ocean floor. 3, metal crack. It can reflect there. So it's a useful one. Are we together? Applications, then you're done. That I wanted to tell you. We already know that we use it to measure the depth. We use it to measure distances. We use it to find the position of cracks. We use it to check for internal structures. So that's a medical thing. Let's just put it again. It's the same things I told you before. The 4 uses of ultra. Main applications, okay? 4 applications, let me say. The 4 applications that we use. Ultrasound. This experiment, number 1, or let's say 3. Let's do 3. We don't have to know 4. You always ask for 3. Number 1, I want you to say it's used sonar for sonar applications, which is check water depth. Then number 2, it is used in medical ultrasound. Medical ultrasound, yes. I don't want that thing on me. Hey, it is not dangerous. Okay? It is non-invasive. I'll tell you why we can use it in medicine, okay? It is not dangerous. So, medical ultrasound, it checks internal body structures. It can check some internal body structures and check them. Then it can be also used in what we call material testing. Material testing. It checks what? Cracks inside a metal. It checks cracks inside a metal. Now, let me just say this, then you'll be done. Here, in medical ultrasound, when you're checking internal body structures, why ultrasound can be used in medicine. It's a sound wave, guys. It's not an electromagnetic wave. It's a sound wave. Reasons are here. 1, it is non-invasive. Can't get in. Number 2, it is believed to be harmless. Even on the skin, it can do nothing. Number 3, it does not use ionizing radiation. It does not use ionizing radiation. Is everybody with me? Guys, does not use ionizing radiation. Ionizing radiation, we know what it is. When we say it's ionizing, it means it can give energy to the cell. That's just in simple, basic. If somebody says, what is ionizing? You say, okay, let me just explain to you in simple words. It doesn't give the cell extra energy, because if the cell gets that extra energy, it can mutate. And mutations, we saw that they can be harmless, they can be beneficial, or they can be dangerous. When are mutations dangerous? If mutation happens to a cell that is dividing, or a cell that is important for cell division, that is gonna be a problem, man. That will cause you some cancer right there. So anyway, we don't want any energy in our body. And ultrasound does not do it. So yes, we can use it then. Wow, this is amazing. I'm proud of all of you. You've gotten to the end, these 3 experiments. This is not, we don't lose our notes. Keep my notes safe. I'll give you a link for you to send me these notes so that I see how you have written. Take your pictures, convert them to PDF, please, and send and upload in Google Classroom. I'm opening the link. Then you'll be graded and I'll give you marks. Before you leave, let me make sure I have attendance because it's going against all your names. So it's part of what your parents see every month at the end of the month to see how much have you attended and how are your marks, because I need it so much to compare your marks with your attendance. Although I don't allow people to be absent, I'm going to start following up on people because I need all of you to get amazing marks. I need it, need it, need it. You guys, I'm counting on you guys. Tobo, are we together? Hope. Good. Litohonolo, are we together? Karabo. KP. Where's Karabo? Kayla. Are we together? Good. Okay. Ano. We meet tomorrow. There's going to be a lot more work. Thank you so much. You've done very well. I'm proud of you as always. Rest. Go and rest. We'll continue tomorrow. Goodbye.